Hi, I will be talking about making a Match2 game in my engine and compare the process of making it on Unity. Alright, let's start with defining a Match2 game. A Match2 game is a puzzle game where the user is given a tile map, and inside these tiles are some objects. If the user clicks on any tile that has at least one adjacent tile of the same type, then click tile and all the adjacent tiles explode and objects that are above them on the tile map fall into their places. There are also some special objects that explode only when certain conditions are met. For example, there is an object that only explodes when it falls to the bottom row of the tile map. The video that I'm showing you is from my run session on Unity Editor, and here is the version that is built on my engine. Let's dive into the development process on each side and talk about the differences. Before we begin, I will not be talking about the logic code and the algorithms to run the game since they remain similar in both methods. I will focus more on how I can implement the features that Unity has on my engine so that my engine can also help with developing a Match2 game. If you are interested in the logic code of the game, you can find them on the GitHub repositories that I linked down below. First things first, we need a way to display the tiles on the screen. Unity has a built-in 2D renderer and a strong UI-driven API, which means to render a quad on screen, all I need to do is right-click on the Hierarchy tab, go to 2D Object, Sprite, Square, and there it is, a quad that we created with like 4 mouse clicks. But how do we draw a quad if we don't have an engine? There are plenty of answers to this question, and we will be focusing on one that includes C++ and OpenGL. As you probably know, we can't just write C++ on Notepad and expect it to work when we press Enter. In other words, we need a compiler. Let's go with Visual Studio 2022 that uses Microsoft C++ compiler. Now that we can compile C++ code, we need some way to create a window that we can operate on. Window creation is a platform-specific task, meaning for each platform like Windows, Mac, Linux, the process will differ. Do we have time or knowledge to implement a solution for all these platforms that we want support just to create a window? No. So we use a third-party library called GLFW. GLFW will not only provide us platform-agnostic window creation functions, it will also offer us some callbacks and methods to listen to user inputs or window size change. So it's good. We like GLFW. Alright, we can write and compile code and create windows now. What else do we need to draw a quad to the screen? I guess we need to talk to that hardware part that draws stuffs and also does some AI shenanigans for a while now. Yes, it is GPU that I'm talking about. And like any other thing on the planet of software, GPU doesn't understand English. So we need another guy called GLAD, which we picked from several other alternatives for the interpreter role. In the case of the communication with GPU, it's not a compilation thing like we faced with C++. The thing is, there are some functions residing in the driver of the GPU, and we want to call them. But we don't know where exactly they are. We could find them ourselves, but GLAD comes to the rescue and saves us time just like GLFW. After we gather all the libraries that we need, link and include them properly, we should be able to compile this code which actually draws a quad on the screen with as little as we can write. Here we initialize GLFW and create our window with GLFW create window. See how easy it is to create a window? Then we set the current context that referred to OpenGL state machine associated with the window. Okay, this might sound a bit confusing. I'm also not sure how all this works, but here's how I see it. OpenGL is just a specification to be followed by GPU manufacturers, so it's nothing more than something like a book of rules. GPU manufacturers read that book and implement them in their GPU drivers. Yeah, the ones everyone says to update if you have low FPS in a game with a 20-year-old GPU. Update your drivers though. The driver runs on your CPU, and when you call an OpenGL function, you actually call the implementation of that function in your driver. OpenGL works as a state machine where it remembers your actions, and when the time comes and a draw call happens, it looks at its state to remember what it needs. So it actually needs to store data on the RAM, and it needs a window because its context is specific to that window. So think of this guy as the GPU driver. Upon receiving OpenGL function calls, he may allocate some memory on the RAM, or he may execute an instruction on the GPU. He just follows the orders of the GPU manufacturer. Now we can access OpenGL functions, and we have a window. Let's draw. The vertices array finally tells us something that we can understand just by looking at it. It defines vertex data for a quad. A vertex is a data structure that describes certain attributes. In this case, they hold the position data for each corner of the quad, but they can hold much more than that. If you look at it line by line, they define a square, each line describing the x, y, z values in order. But why minus 0.5 and where on my window is minus 0.5? Enter normalized device coordinates. OpenGL only processes coordinates that are within normalized device coordinates, which is a range between -1 and 1. So if a coordinate is not within this range, it will not be visible on the screen. We can try this out by setting x-coordinate of the lower left vertex to -1.5. As you can see, coordinates outside of the range are not visible. Even though I'm defining a quad that should look like a square, it doesn't. And the reason is, these coordinates are more like a proportion as they are now. That -0.5 is saying that start from the left of the window and go right by the quarter of the total width of the screen. To make it actually look like a square, we need to take aspect ratio of our window into consideration. We can do this by dividing each x-coordinate of our vertices by the aspect ratio, and we will get our square. But this is not what we do in practice. Instead, we introduce cameras. More on that later. To finalize the quad drawing part, we send this vertex data to the GPU using these functions, and issue a draw call at each frame of our application. When a draw call is issued, OpenGL makes necessary adjustments using this state information and takes our input through its rendering pipeline. As a result, it produces pixel values to create images on screen. Let's get to the next challenge. In Unity, I can adjust the position of a quad by dragging it. I can also draw multiple quads to form a tile map. So, the next objective is to implement this in our application. At this part, we are introduced to what I think to be the most magical part of 2D rendering, as far as my knowledge goes. Mathematics. And to be more specific, matrices. Using matrices, we do all kinds of modifications to our vertices. Before we dive deeper into everyone's favorite subject, we need a library to help us with mathematical operations. And we will use GLM for this. GLM is a mathematics library based on OpenGL shading language, GLSL. So, what is it with those matrices? Well, let me explain. This is the vertex data of our quad from before. Let's say we want to move it to right by 0.5 units. All we need to do is to add 0.5 to the x-coordinates of our vertices, right? Yes, that's right actually. But there's another way. We can generate a matrix that translates each vertex of our quad. Why we might want to do that, you may wonder. Because they are perfect for containing the modifications that we want to do. For example, if we want to move our object first, then apply a rotation on x-axis, then apply a projection to it, we can store that all in one matrix by multiplying each matrix considering the order. Then, if we multiply a vertex with the resulting single matrix, it will apply all the modifications. Matrices not only help us store modifications, they are also highly efficient since the data is tightly packed. At this point, we can talk about the camera. Camera is at the minimum level nothing more than the multiplication of view and projection matrices. There is no such thing as camera in OpenGL or any other rendering API. If we want the camera to move left, essentially we just move everything to right. After applying all that we've talked, we can render a tile map on screen. Let's take a cursory glance to the code to see what's going on. First of all, we can see that our file got bigger. Outside of main, we defined some static functions to listen for GLFW callbacks. In main, we have provided some source code for our shaders and asked OpenGL to compile and link this source code to a shader program. Here is where we defined our vertices, and this time we also defined indices that indicate drawing order for vertices. In this section, we defined some transform data using GLM for our tiles and the camera, and as the last step, we drove the tile map by issuing a draw call for each tile to be drawn. Let's see how we are able to define transform data for our tiles and the camera. The magic happens in this line, where we multiply translation and scale matrix to get our model matrix. This says that first translate all the vertices by the values that are defined in the tile position vector, then apply a scaling factor using the scale vector. As we can see, our scale vector says that scale the object by 0.8 on x and y axis, and don't change to the z axis. The position vector starts the position of the first tile at 0 to 0, and we increment the x and y values accordingly in the nested loop. We adjust the position vector of the camera when a key press happens and generate a translation matrix that takes the negative of camera's position vector as the argument, because we want to move everything in the opposite direction of the camera. Lastly, we are able to adjust the zoom level variable using our scroll wheel, thanks to the callback functions that we defined and use it in the orthographic projection generation to zoom in and out of the screen. By multiplying these three matrices, we get a matrix that holds all of our transformations, and we send this matrix to our shader to let GPU multiply each vertex with this matrix, because GPU can do this all in parallel, resulting in much faster process time. Okay, as the project goes on, some problems arise. The code is around 230 lines as it is, and there are many things that we need to add. We need to design our code base for it to be more scalable. For example, what happens when we try to add texture to these tiles, or how will we handle the movement of a tile when a match happens? We don't even have a definition for a tile, it's just a 3D point on the coordinate system. Not to forget, we need to separate the game logic from rendering. I need to mention that we don't have to do all this to make a Match2 game. Not every game has to be developed on some kind of generalist game engine. Just some abstraction for OpenGL primitives may suffice if your goal is to make a game using OpenGL. So back to our problem. How do we make things more scalable? Imagine instead of writing all this code to render tile on the screen, we had to write just this one line of code. Or instead of creating a shader by doing all these operations, we had to just write this. This is where we start to cross the line between game or graphics programming to game engine programming. It is not possible for me to develop a game engine that can compete with other ones on the market. The scale of these engines are huge, but I can develop a generalist engine but still specific to my needs on some areas. After I spent 6 months tussling with YouTube tutorials, thank you Cherno, I was able to complete a game engine that can make a Match2 game. With my engine, I was ready for the next step to implement in the game. Clicking on tiles. Unity handles the clicking by its colliders. When I add a collider to a GameObject transform, that GameObject is now listening for collision. Next step to do in Unity is to send a ray from the mouse to the scene. Unity has helper functions to convert the mouse position, which is the X and Y pixel positions, to world position. After we get the world position of our mouse, we send a ray from the mouse position to the world, and if the ray hits a collider, we can get the information of the tile that the collider is bound to. So how can I implement this in my engine? Let's start with what I can get as of this state. Only thing I have right now is the screen position of the mouse in the window, and I can also listen to mouse clicks thanks to GLFW. First thing to do is to convert screen position of the mouse to normalized device coordinates. After that, I need to get the resulting point to world space. Things like this are easier to understand with examples, so my remarkable handwriting is here to help us. The normalized device coordinates that we get doesn't take camera's position and projection into consideration. Thus, we cannot use it on our logical calculations that interact with objects on the world. We need to get the point into the world, and we do that by reversing the transformation that the camera does to any vertex that we have. We achieve this by multiplying our points with the inverse of the view and projection matrices of the camera. Yes, multiplying by the inverse reverses the transformation that was done by that matrix. See why I consider matrices to be so magical? Alright, next step is to send a ray from the world position of the mouse towards the scene. First of all, what is a ray? Ray is just a structure that has an origin and a direction. If we set the origin of the ray to the mouse's world position and set the direction to be a direction vector that is perpendicular to our camera, we can check if it hits to any object in the scene. Now let's think. We have a ray and a quad. How do you know if the ray hits it? Since our game is 2D, it is easier to imagine the process. If the x and y values of the origin of our ray are within the bounds of our quad, and the z value of the position of our quad minus the origin of the ray is negative, that means we got a hit. But what if the quad is rotated or scaled? Yes, we know the position of the quad, but not the corners of it. At this point, we swing the magic wand once more and transfer the ray to the local space of the quad. We do this by multiplying the ray with the inverse of quad's transformation matrix. In the local space, the quad is not rotated, scaled, or translated, and we know each corner's position. Now we can do a basic bound check to see if the ray hits the quad or not. By the way, this code you see is from my engine. You see there's a type called GameEntity, which has another class called Transform. Transform class allows us to define a transformation for an entity, along with storing the transformation data as a matrix for future use. And as we can see, we use it to get our ray to the entities, which is our quad's local space. So things like that are what makes a game engine. After I covered raycast, there is actually not much left that I can talk about without being too technical or drowning in the details. From this point on, if you implement a solid object generation and disposal system, only thing left will be to implement the logic code of the Match2 game and you are done. Before I end the video, I want to talk about a technical improvement that makes a better performant engine because things like this excites me. I want to cover batch rendering and how it's different than what we were doing so far. Let me first make a demonstration showing the latest state of the game. Here we can see how many draw calls are issued in one frame. For 129 quads, we issue 129 draw calls. So we issue a draw call for each quad that we want to draw. Draw calls are not that cheap processes. The GPU makes a whole preparation when it needs to draw something on a screen. We get around 300 to 500 FPS with this way. Let's look at the other option. What if we could draw all this in just one call? Let me change the rendering method from snap rendering to batch rendering, and let's see the results. Now we draw 129 quad in one call and our FPS is around 500 to 700. Here's how. When we use snap rendering methods, I made up the name by the way, what we do is as follows. We define a vertex data for a quad and send it to GPU. Then each frame we tell the GPU to draw it. We also send another data which is called a uniform. Uniforms are another way that we can transfer data to GPU. They are faster compared to sending vertex data through vertex buffer, so they don't hurt our performance that much, and they are a valid way to transfer data. We send a model matrix for each quad that we want to draw since we don't want them all to be at the same position, rotation and scale. Then, at each frame, the GPU takes the vertex data, which is static for each draw call, multiplies it with the model matrix, which changes at each call, and draws it to screen. Okay, so what is batch rendering then? As I said, we send vertex data to GPU and we keep it in VRAM, which is GPU's RAM. VRAMs are huge and they can hold all the vertex data that construct your favorite character in a video game. And unlike quads, a humanoid character is much more than 4 vertices if I'm not mistaken. So why waste all that space? We can send all the quads in our scene by a vertex buffer to GPU, but we need to set their location by multiplying with the model matrix on the CPU, which is favorable since issuing a draw call for each quad is much less performant. This is what batch rendering is. By using it, we get rid of sending uniform data to GPU each frame, and we render all our quads in one draw call. That pretty much covers the topics that I want to talk about on developing a game engine and making a game on it. I hope I have managed to convey these sometimes difficult to explain topics to you in an easily understandable way. Thank you for listening.